Cool. Let's begin. And maybe I'll begin with just a reminder of some stuff that you've had and maybe should have looked at a little bit by now. Next week is that midterm. You've had some time to look at those review questions for the midterm. People have any concerns about it? Okay. As a reminder, if you think everything's fine and you find some of the questions uninspiring, there's one bit of motivation to look hard at it. If you find anything that looks like just a straight mistake I've made in there, point it out to me. There's a spot in Canvas to upload it. If it's an error no one else has found yet, look at some points. And at this point, only one error on that document has been pointed out. So, I'm sure there's still lots more because I know me. I refuse to think there's nothing else that's just wrong in that document. So, let's talk about inverse functions. And maybe I'll take a tour of this document and then we'll talk through it because I want to start in on also a new topic today, namely exponentials. So, we're going to go ahead and find one inverse function. We'll follow the same algebraic set of instructions as usual to do it. And we'll compare that with some stuff about graphs of inverse functions. And that we'll check this answer by using a graph. And then we'll also think about things like what do domain, range, vertical asymptotes, horizontal asymptotes do when you take inverse functions. And the answer to all of it is, well, the x and y values swap, so that tells you. The last thing I'm going to do is, well, what's really the definition of an inverse function? It's something about composition. So if you really want to know an inverse function is something you think it is, you have to compute some compositions. And as motivation, there's an open-ended homework posted for this unit, and it'll basically be that idea. So let's talk through it. All right, so let's compute the inverse function for that function, x minus 1 all over x minus 2. What's the algebraic idea you use if you want to find an inverse function? Well, I guess the motivation is even in this line. I'm going to swap x's and y's, and what would that give me? Instead of thinking of this as y is the output, when you swap x and y, you get x equals y minus 1 over y minus 2. Cool. And then what should you do? Cool, yeah, that's even the first step. I want to solve this for y. Yeah, so let's cross multiply because that's going to give us progress towards that. Most annoying thing I see is division, so let's cross multiply. Alright, cool. There's at least no division anymore. And I want to keep getting y on its own. And maybe I'll see how people feel after that first step. I don't you just do it and you'll tell me the answer in a little bit, or I should keep talking. Should I actually talk through the algebra from this point? Cool, seeing some heads nodding, I'll do it. So, that's where we are. I want to solve for y. So I want to get y on its own. So it seems like a good idea now. So I think I want to get all the y's onto the same side, get all the things that don't involve y onto the other side. But before I can do that, the y is trapped inside those parentheses. So I think I want to get rid of those parentheses. So what should I do? Distribute the x. Do the instructions that the parentheses tell you. xy minus 2x equals y minus 1. Alright. And now I want to get all the y's onto one side, all of the non-y's onto the other. So let's just see. There's a term that involves y. There's a term that involves y. The other two terms don't involve y. So it seems like a good idea. I guess the choice is get all the y's onto the left or all the y's onto the right. And it doesn't really matter which we pick. How many people would rather move the y's onto the right? Move the y's onto the left. Cool. The onto the lefts, I think, had it. It doesn't really make a difference. Let's move all the y's onto the left. So I guess I need to subtract y to the other side, so I'll subtract y onto this side. Let's add 2x to the other side to get it off of the side where it is now. And let's see what we're left with. We now have xy minus y equals 2x minus 1. All right, cool. What next? Well, eventually my goal is like get y on its own, right? So right now I see like two things that have a y, but they have like the same kind of y. So what can I do to make it so there's only one y?
Can you divide by x?
I could. You can certainly always divide both sides by x. So that's like not a wrong idea, but I think I'm going to try to say why it's a bad idea. So if you divide both sides by x, then on this side, these x's don't cancel because there's a minus y over there. So you'd certainly wind up with a y, but then you'd wind up with something like that, which it doesn't help, but think about what you could divide by. And let's think about it by this. Everything on the complicated looking side, xy minus y. Everything on the side with the y's, everything on that side has a y. So everything's multiplied by y, so what can I do?
Take a y out.
And then I'll see what I should divide by. So let's say, I guess that's x minus 1 y. All right, well that looks pretty good now, doesn't it? What should I do next? Divide by the stuff that's multiplied by y. Awesome. Y equals 2x minus 1 over x minus 1. Oh, groovy. That feel like it went pretty okay? And in fact, let's box that. Maybe I'll write the conclusion too. So that means that f inverse of x ought to be 2x minus 1 over x minus 1. And what do you think? Could you have done this for like basically any function that looked like linear function divided by linear function? Yeah, maybe there's like an exception if like it turns out that linear function divided by linear function is like constant. But like, as long as that doesn't happen, you can always do that. Extra credit. Derive a formula that inverts any function that looks like this. It's in the notes, probably somewhere after this section. Nice. So there's the inverse function. Let's check that. The inverse function should do something with the graph. So let's see if it does the right thing with the graph. Come on, that's not helpful. All right, cool. So there's the function we just graphed. Let's also graph this alleged inverse function. And let's just eyeball that for a moment. After I correct it. Do these things look like they're the same? They're just the x's and y's have been swapped? Yeah, and like there's a way you can eyeball a few things. 1, 0 should become 0, 1. That's on there. I guess these points where they cross had better be like the same x value as y value because they're going to flip to themselves. Yep, they seem to do that. Let's think about some other things we could do. Well, these two things should literally be the same, just the x's and y's are swapped. Yeah.
Could you graph y equals x and see if it reflects over that?
Oh, sure, that's a good idea too. I want it dashed. Yeah, so does it look like the red and the blue are symmetric over that line? Yeah, that looks convincing too. Here's another bit of shtick we can do. There's the alleged inverse function. You can literally take this, and Desmos doesn't care if x is the independent variable or y. So you can swap the x's and y's. That ought to be the same as the graph of the inverse function. It looks like it is. Cool. So I believe this is correct. And with that in mind, that's just a reminder that if I ask you to find an inverse function, you can check your answer. All right. So let's read off a few more things. Maybe we'll be motivated by this a little bit. Let's talk about domains and ranges. If I give you any graph, how do you read the domain from the graph?
All x values on the graph.
All x values on the graph. How about the range? The y values. Cool. Well, the graphs of f and f inverse differ by just swapping x and y values. So let's think about what that means. If I give you a one-to-one function and ask you for the domain of the inverse function, I'm going to write a few steps. That's going to be like all of the x values on y equals f inverse of x. Fair enough? Ooh, but I could express that in terms of the original function too. That's the same as all of the y values on the graph of y equals f of x. All right. We already have a name for all the y values on y equals f of x. What's the name for that?
Range.
The range. Cool. So here's the point. If I ask you for the domain of an inverse function, that's the same as the range of the original function. And you don't even have to find the inverse function to compute that then. Just look at the original function, figure out what things are not in the domain. Those will be the things that won't be in the range of the inverse. And the opposite's also true. The range of an inverse function is the same as the domain of the original function. That feel pretty sensible? And let's do a quick discussion sanity check. So I'm going to want to copy this example down onto the next page, just the start and end. X minus 1, x minus 2. Okay, so for f of x equals x minus 1, x minus 2, we got f inverse of x to be 2x minus 1 over x minus 1. Yes. All I did is copy down the function from the previous page so far. Yeah, that's good. Let's check off if that walks correctly. Let's determine domain and range of this function and the inverse function, and see if these things agree. Well, that's like a division problem. So what's the only thing not in the domain of this thing? 2. X equals 2 is the only thing not in the domain. If you picture the graph of this thing, well, you know what the graph will look like. It'll be like, I don't really care where. It'll look something like that. Some shifted, maybe flipped copy of 1 over x. So the only thing not in the range is the horizontal asymptote. This thing never crosses its horizontal asymptote. Some things do, this doesn't. Where's the horizontal asymptote of this thing? What's the degree of the numerator? What's the degree of the denominator? Both ones. And what are the leading coefficients?
1.
Both 1. So where's the horizontal asymptote? At 1. It's 1 over 1. So the only thing not in the range of the original function is y equals 1. Let's see if that agrees. There's the inverse function. So by looking at that inverse function, what's the only thing not in the domain of that inverse function?
X.
Nice. The domain of the inverse function agrees with the range of the original. And now let's go the other way. The only thing not in the range of this thing will be the horizontal asymptote. Where's the horizontal asymptote? At 2. Oh, cool. Yeah, it checks out. All right, one last thing I want to do with inverse functions. So here is the most mathematically complete, correct, and rigorous definition of an inverse function. So an inverse function is supposed to undo the original function. And here's the definition of what it really means to undo a function. If I give you a function f of x, the inverse function f inverse of x is the unique function that satisfies that if you take the original function and do it to x, and then you undo it, you should always get x back. If you do the inverse function and then do f, so if you undo f and then do it, you should also always get x. So really, if you want to check, so what's the point? If you want to check that an inverse function is correct, you need to compute some composition. Fair enough. So, let's go through and do this for the example that we've just done. Let's check that the inverse function to the function that we computed the inverse function to is the function that we think it should be. So, to do this, I guess we need to check that f of f inverse of x is x. And we need to check that f inverse of f of x is also equal to x. So we need to do like 2 compositions. And I think it's worth spending a couple minutes right now. Let's compute at least one of them. And so we'll pick one and I'll do that one, and I guess like writing this all up is going to be some homework. So, should I do the first one? Second one? Cool, I think it was like 2 to 1 in favor of the second one. They'll both be about the same amount of complexity. So, let's do it. Let's check this one. Let's compute f inverse of f of x and check that we can simplify it down to just x. F inverse of, I like to color code these a little bit. Alright, so how do you do function composition? We've got a formula for f inverse of x. It's at the top of the page. Oh, it's also like right there. Let's use that. So that will be 2x minus 1 all over x minus 1. But I don't want to put x there. I want to put f of x there. And I've also got a formula for f of x. It's that. And assuming that nothing went wrong while computing the inverse, which I don't think it did, because like the graph agreed, that should simplify down to just x. So let's try to simplify it. There are a few paths to take. If you want to see this in the wild, what would you want to do to simplify? let's think about what makes this annoying. I see like complicated stuff in the numerator and complicated stuff in the denominator. So let's focus on just the numerator right now. If you just saw this numerator and I said simplify this, what would you do?
Factor.
What do you mean by factor?
Multiply the 2 by x minus 1, x minus 2.
Oh, cool. So anti-factor, distribute.
Yeah, it's true.
So yeah, let's distribute that 2 through it. And let's see, the 2 gets multiplied onto the numerator because that's how you multiply a number by a fraction. I'll see 2x minus 2 all over x minus 2 minus 1. And what about in the denominator? Do you see anything you could do that's useful there? Let's see, I see a fraction minus 1. So how do you add or subtract fractions? Get a common denominator. In this case, what is that common denominator? X minus 2. And I guess I'm going to have to do that in the numerator also. In fact, do people object to me also getting a common denominator in the numerator in this step? I'll do it in the next step. You can do it right now if you want to. X minus 1 over x minus 2 minus x minus 2 over x minus 2. And I'm going to start putting parentheses so I can distinguish the big division from the little divisions. All right, nice. I guess now we may as well do the same thing in the numerator that we just did in the denominator. 2x minus 2 minus, well, all over x minus 2 minus x minus 2 over x minus 2. And, all right, cool. The whole point of getting common denominators is so you can add or subtract fractions. So what does just the denominator, what does just this piece simplify to?
X minus 1 minus x minus 2 all over x minus 2.
Awesome. X minus 1 minus x minus 2, and you need those parentheses because you want to subtract all of x minus 2, all over x minus 2. Alrighty, that's something. And let's just keep going. Keep on following your nose. What should I do next?
Combine like terms.
Oh, sure. In this piece, you mean?
Yeah.
Yeah, let's do that. Let's also do something in the numerator. So, I guess you told me what to do in the denominator, combine like terms. I guess I'm going to see an x minus x, so how many x's? 0. So no x's, minus 1 minus minus 2. So minus 1 plus 2 is 1. All right, 1 over x minus 2. All right, well, I guess that's the same as just multiplying by x minus 2, but I can hold on to that for a later step. What about the numerator? What can I do there? Well, the numerator is just like a step behind the denominator, right? So let's do the same things we just did in the denominator. Arguably, probably we should have synced up these steps, but. So, everything is divided by x minus 2. And what do I see? I see 2x minus 2 minus x minus 2. Cool, plugging along. All right, let's just keep on going. And I know what my goal is. I think this should simplify down to x. So, let's just keep going. So you see all of that written down. Tell me some stuff.
If you combine like terms on it. Yeah, it's x.
Yeah, cool. 2x minus x leaves me with just x. Minus 2 minus minus 2 is 0. All right. Yeah.
Because it has an x minus 2 on both the numerator and denominator, can you get good with this?
Yeah, right. If you divide the numerator and denominator by 7, that resolves the value of the thing. Right? You can always multiply or divide all of the numerator by a number. So these two cancel. You're left with x over 1. Oh, cool, that's just x. So we're done. So f inverse of f of x is actually equal to x, as we still need to do one more thing, or maybe we's the wrong one. You still need to do one more thing. Same thing should happen if you do the other. Cool. Any people follow like a fundamentally different order of doing this? Yeah, okay, you could have. There were a few options. One option you could have done is, well, you notice in the top I see a denominator, sorry, of x minus 2 in the top and in the bottom. Oh, so could I have multiplied the whole big fraction by x minus 2 over x minus 2? That might have been helpful. There's more than one way to shake this stick. That's the saying, I think. All right. So, any questions before I move on? Nice. So, a bunch of the homework associated with this particular topic is do this. For this exact same example, I think. So let's take that. Let's move on to one new flavor of function. Let's talk about exponential functions. And let's see, if I say exponential function, how many people have some idea what I mean? Cool. What's an exponential function? Yeah.
It just increases like naturally, I guess.
Yeah, it's a function that they tend to increase like quickly. More quickly than any polynomials. There are things that increase more quickly. How many people have studied factorials at some point in their life? Yeah, so factorial is like the function that's defined by n factorial is you multiply together all of the whole numbers less than or equal to n. And that turns out to grow faster than any exponential. So it grows real fast. And usually it's like the fastest growing thing that you'll see reflected in natural world over short periods of time. But there are other things that like do grow faster. So let's introduce exponentials. They're a particular flavor of quickly growing thing. And let's introduce them, in fact, by a single chemistry and physics example. Let's talk about radioactive decay. So, there is a radioactive element, americium-240. This element has a half-life of about 2 days. As I found by looking at the Wikipedia article for interesting radioactive elements listed by half-life, I wanted something that was on the order of days. And then I rounded off most of the digits because this isn't actually a physics or chemistry class. So let's take what that means. So what the half-life tells you is radioactive particles, they behave really probabilistically. Any given atom of americium-240 has a 50% chance of breaking down into smaller pieces over the course of 2 days. But when you have an amount of a substance, you've got a whole lot of elements. So the fact that each one has a 50% probability of decaying means that over a day, half of it will decay. Law of large numbers says that as soon as you have enough of something, probability is the same as the proportion. So let's see what that means. So in any 2-day period, half of it will decay. You start with 1 kilogram. Then let's just analyze how much is left after any amount of time. After 2 days, All of those should be in days. After 2 days, half of it will have decayed. So you started with 1,000 grams because that's a kilogram, now you have 500 grams. You wait another 2 days, you have 250 grams left. How about at 6 days? How about at 8 days?
62.5.
62.5, whatever half of the previous number was. How about at 10 days?
31.25.
That sounds right. Whatever you get by dividing by 2 again. Alright, cool. So let's suppose that all of these instances of hour should be days. I think that's the amount that I want. Yeah. In general, if I tell you that I have waited an even number of days, so 2n many days, how do you determine how much of the substance should remain? Let's see, when you waited 2 days once, you divide by 2. When you wait 2 days twice, you divide by 2 twice. When you wait 2 days 3 times, you divide by 2 3 times. So if I tell you you have waited 2 days n many times, how many times do you divide by 2? N. So, if you want to know how much is left, well, you started with that 1,000 grams, and you divide by 2 n many times. Cool, that feel pretty alright? And let's just notice there's some this is a common enough thing to do that there's some notation for this. Well, when you take 2 and multiply it by a bunch of times, that's what exponential functions are. Exponential functions are things that are modeled after multiplied by a number, a variable number of times. It's also useful to think about negative powers. Another way that's written, just another notation that means the same thing, 1,000 times 2 to the negative n. Right, if you want to divide by 2 a bunch of times, that's the same thing as anti-multiplying by 2 a bunch of times. So negative powers, they correspond to division. What about this? What if I don't tell you that it's been 2n many days, but I just say it's an amount of t measured in days? Then what? It's how would you figure out how much is left at 1 day? Let's think about this formula. So I know how much is left at 2n many days. Well, I want t to be 2n. And right now I have a formula that has n in it. Does that look like something you could solve for n? Yeah, what do you get? T over 2 is n. Oh, cool. So I can take this formula and plug it into, that one's more compact, that expression. 1,000 grams times 2 to the negative t over 2. Nice. So that means if I want to know how much is left at 1 day, well, it looks like I need 1,000 multiplied by 2 to the negative 1/2. Alright, well, suddenly that's not a whole number I'm dividing by. So I think at this point, I bust out a calculator if I want that decimal approximation. You grab the one you like. I'll use the one that I've tended to be using right now. In fact, you know what? I want to do enough calculatory things today. One 1,000 times 2 raised to the negative 1/2. About 707 grams. And in fact, let's just acknowledge one thing. If this is supposed to be like a real world problem, there's no such thing really as exactly 1,000 grams. All of these things are really approximate. We'll take a moment. You've got a calculator, be it a laptop or like a handheld. Fill in the remaining entries in that table. Let's see what we get. Yeah, what do we get? I guess this is a less exciting exercise for those who don't carry computer machines on them. So let's fill these in. At t equals 3 days.
354.
154?
354.
That seems more reasonable. It probably should be somewhere between 500 and 250. All right, at t equals 5 days. About 177. T equals 7.
88.4.
About 88.4 days. Sorry, 88.4 grams. Mass is in grams, not days. At t equals 9 days.
44.2.
Cool. That feel pretty alright? Nice. Alright, so let's start varying this a little bit. Let's suppose I have you wait 25 hours, also known as 1 day and 1 hour. How would you figure out the amount left then? Let's see, I guess it's like a fractional number of days, right? How do you figure out what that fractional number is if you wait 25 hours? Yeah.
Could you just add like 1/24?
That seems reasonable. 1 day plus 1 hour. Well, it's the same thing as 1 day plus 1/24th of a day, because 1 hour is 1/24th of a day. Cool. So it looks like that's what I want to plug in for t. Let's do that. Cool. So the t value is 25 over 24, and I know that I could like simplify that some. Right, that's the same thing as 25/12ths. Nope. You divide 25/48ths. So what do I get? I get 1,000 grams times 2 to the negative 25 over 24 over 2, which apparently is about, goodness, 697 grams. All right, neato. Let's go more complicated by one yet. Let's really think about unit conversions here. 5 hours, 42 minutes, and 3 seconds. Well, I guess I have to convert these one at a time. What's 5 hours? How do you get from hours to days? Each hour is 1/24th of a day? So maybe I'll even like, a convenient way to sort this information is to think about 5 hours and multiply it by 1. But I want to multiply it by 1 in a way that gets rid of hours and introduces days. 24 hours is 1 day, so I've just multiplied by 1. Alright, let's play the same game again. 42 minutes. Alright, so I know how to convert from hours to days, so if I can convert from minutes to hours, then I can go from minutes to hours to days. How many minutes to the hour? 60. So 32 minutes. I want to get something that gets rid of the minutes, so I want to divide by minutes, introduces hours. 1 hour is 60 minutes, so there's multiplying by 1. And it's also 60 hours to 1 day. What?
24 hours.
24 hours to a day. That's kind of silly. All right. Oh, 24, not 25. All right, so now I have to actually multiply something harder. 6 times 4 is another 24. Carry the 2. 2040. Is that the denominator now?
Yeah, 1440.
I know what I did. Thank you. All right, cool. All right, and how about 30 seconds? That's going to be like a small number. So let's see, 30 seconds. Goodness, that's 30 seconds. Let's convert to minutes. 1 minute plus 60 seconds. 1 hour per 30 minutes. 1 day per 24 hours. So during the course of,
1 hour for 60 minutes?
Jesus. I do know how to read a clock. So it's actually interesting. One of the the origin of is there another just screw up there? Okay, that's it. The origin of the metric system has a lot to do with stuff that happened during the French Revolution. They wanted to standardize things, and so they did. And a lot of that's really useful. They also standardized time measurements. That didn't catch on because people didn't like the 10-day week. But right, 10 hours to a day, 10 minutes to an hour, probably 1,000 seconds to one of those minutes. That would be convenient, wouldn't it? Anyway. You get whatever it is you get. How many people have already done that for me so I don't have to, because I'm going to get it wrong anyway. Alright, so what's the amount of days that have passed? It's 5 over 24, plus the next thing, plus the next thing. Goodness. 86400. Alright, about 0.23 days. And in fact, if I wanted that much precision, I probably could have ignored the seconds anyway. So, you want to know how much of the substance is left after this time? Plug in that t value. You'll get what you get. Groovy. So, what's the point here? The point here is, if you want to think about things that decay exponentially, you need to think about exponential functions. Makes sense. If you want to evaluate those, on the one hand, you definitely can whenever you see a whole number in the exponent. You just multiply and divide that many times. If you want to plug in something else, yeah, probably you need to resort to a machine at some point. The machine is doing something clever. It's using what's called a Taylor series for 2 to the x. And Taylor series are something that you'll learn a lot about in calculus 2. And let's see, with 5 minutes left, let's start just building some formality about this. All right, I got 5 minutes. If I give you an exponential function b to the x, and I just ask you to plug in a whole number, you already know what you're supposed to do. B to the n is just b times da 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 times b n times. If you want to plug in a negative power, well, that's division by b that many times. You might also think of it as 1 over b times 1 over b that many times. Fair enough. And I guess there are a few things to note there. So that means this is the same thing as 1 over b to the n. B to the negative n, you can make the power positive by dividing by whatever is in the base. Or 1 over b to the n. You can just move that n right into the denominator if you want. That seems sensible? Nice. So we're getting even like some rules that exponential functions follow. Zero power. So you kind of have to just like decide what you want the zero power to be, and there's a canonical choice. So if b to the n means multiplied by b a bunch of times, then b to the 0 should be what you get if you don't multiply by b any times. So what do you think it should be? 1 seems right. How many people would have wanted it to be 0? It's certainly an intuitive choice, but 1 works out to be the more reasonable one because, well, if I do b to the 0 and multiply it by b, that should be like you've multiplied by b 1 times. So something times b has to be b. Yeah, b to the 0 has to be 1. Provided that b isn't 0, I will forbid you from ever talking about 0 to the power 0. It is not something that is defined. You can try to figure out definitions, but depending on like how you walk out what you want it to be, really you can argue that it should be anything. Which is why we just don't talk about it. Rational powers. If you take a rational power and a positive base, so you don't accidentally wind up taking a square root of a negative or something, then b to the p over q, I'm going to define that to be take the qth root of b to the power p, or take the qth root of b and then raise it to the power p. And you'll notice that those things can get complicated enough that you don't want to compute that by hand most of the time. So usually, we'll resort to a calculator pretty quick if we want to actually evaluate an exponential. On the other hand, there are sometimes that we can just do things on the nose. Let's jump a little bit around. 8 to the 5 over 3. Let's try to compute that using this definition. So that means I want to take 8, 1 over 3. So I want to take the cube root of 8, and then I want to take that to the 5th power. Do you know the cube root of 8? 2, because 2 times 2 times 2 is 8. That's 2 to the 5th power. Oh, how many people feel like they have their powers of 2s more or less memorized up to some amount? Yeah, it's worth it. How many people in here are like computer science-y people? Yeah, then you definitely should know your powers of 2. They come up enough. 2 to the 5th is 42, right? 2, 4, 8, 16, 42. So you can compute some on the nose. Notice, there are irrational numbers. I haven't told you how to make sense of those. Making sense of them, really what you think about is, well, the square root of 2 is like 1.707-ish or something. Yeah, it's got a decimal expansion. So just write out the first like 10 digits of that decimal expansion. That's a rational number. Follow these instructions for that rational number. There's a way of defining it. You definitely don't want to do that by hand. So really, if you want to compute anything like that, use the computer. Our computer is going to use a power series, and it'll give you like this. Nice. So, I am out of time. So, as people pack up, what are some relevant announcements? Homework's due today. You've got those things for that final exam to look at for that review. And there's that, like, in Canvas 4 points practice document. You should take a look at that. I'm also going to post solutions to that PDF review probably sometime today. Now, let's stop the recording.